Everyone. In this session, we will look at reinforcement learning, and on the lecture, we will take rather more superficial view of different algorithms on the reinforcement learning, and then later on, it will be followed up by discussion of case studies in terms of robot motion planning using reinforcement learning algorithms. And that time, we will to dive into further details or the mathematical aspect of individual algorithm. Now, this reinforcement learning, it may be or it may seem a bit new or to the community in robotics or the community of computing, but reinforcement learning on its own has been very highly investigated by pedagogists or animal psychologists because our brain is often an inductive learner, and psychologists, they often try to teach animals to undertake tasks by giving them positive or negative rewards, or as the kids are also grow up, if we look at the context of pedagogy, that sometimes even unconsciously we give some sort of reward to the kid, or sometimes we scold the kid in the school. Maybe I will also do it to you, to give them positive and negative reward to indicate them what is good, what is bad, because in philosophical sense also it's many times it's dubious that what is good, what is bad. So I cannot tell in abstract term or very explicit terms, so rather we give some indication. So in the rest part of the lecture, we will see that how we can mathematically encode that and teach a machine in similar way. And later on, we will make it far closer to human learning when we will talk about imitation learning. Moving on. In the next hour or so, we'll first look at the introduction more from a mathematical point of view, or contextualize it with other machine learning techniques, that how reinforcement learning is different or similar to supervised or unsupervised learning. On the very first class, we had a very brief discussion on different types of machine learning. And then we will learn about three types of passive reinforcement learning algorithm. And in this case, I will mostly follow the notation of the book by Russell Novick, A Modern Approach to Artificial Intelligence. It's here. And then we will have a comparison of these three algorithms: the direct utility estimation, adaptive dynamic programming, shortened as ADP, and temporal difference learning. And after that, we will go into the active reinforcement learning. So in subsequently, I will discuss the difference between the passive and active reinforcement learning. And we will learn about Q learning and multi-arm bandit problem, which is a very well-known problem. And it will be followed up by discussion of some case studies where our students developed scheduling algorithm using the concept of multi-arm bandit problem. And finally, we will very briefly introduce you with some advanced reinforcement learning concepts like the deep Q learning, which you may find some resemblance with the direct utility estimation when we will discuss. Then inverse reinforcement learning, mainly one of my PhD students, Mukund, he is doing PhD on imitation learning. So he will take a session on inverse reinforcement learning and its applications to mixed reality interfaces and for human robot handover request. And of course, we will show you demonstrations. And during that time, we will go into further detail on explaining the algorithms. So in terms of mathematical introduction, that when we looked at supervised, unsupervised learning, we talk about that in one case, we have training samples. In another case, we do not have training sample. And in reinforcement learning, the algorithms will be explained in a context that where there will be an agent. So in a motion planning class, you can consider the agent is being a robot, like a moving bot or a fixed base bot, or maybe a flying bot like a drone. Or it is not confined to a physical agent. The agent can be also a software agent, like when, say, we are developing a virtual game player for a game. And then there will be an environment. We will go into further details that how we encode environment or what its effects on the algorithm in subsequent slides. But this agent will act on the environment And based on this action, the environment will respond back, and the agent will perceive this. If you uh, briefly remember that in the MDP lecture, we indeed discussed about this cognitive model, and in turn, the agent will perceive this new state, and also it will get some sort of reward, which will be an indication to that how good is the action or how near it is to the goal state. So the goal will be a function on the state fx equal to y, and the data will be in the form of x1, y1, something like that, where y is the reward. Here, what we will try, which is very similar to our value iteration or policy iteration algorithm that we discussed earlier, that we try to maximize the reward for a pair of state and action, and the data will be given in the form of this reward and state. So unlike as we discussed during the value and policy iteration class, that we will not know the model or the state transition probability matrix. Rather, we will be given data as the agent is perceiving the environment, and we will try to maximize the reward. And of course, the ultimate aim will be to go to the goal state. In some cases, we will try to take it near to the goal state when the goal state is not very well known. So if we just look back the examples of this supervised learning and unsupervised learning, that in supervised learning, the training data we get in the terms of observation measurements, and we know that what we want to get out of it. So we train a model, and the main trouble here is that often our observation or measurements that has some inherent error, either due to the measurement accuracy or transmission accuracy, or maybe for many other reasons. And we try to fit a model where we can minimize that error. But we know that what we want to get. In unsupervised learning or clustering, the class levels of data are of course unknown. So we have the data, and based on the distance metric among the data, we try to segregate the data. And the distance is measured based on a set of features of the data. In case of reinforcement learning, that we get the best reward or the goal when we get the +1 or -1 reward once we reach the goal state. So at the present, like the supervised learning, we do not immediately get the benefit of our action. We give some indication in the form of reward, but that is just an indication. That is not the final reward. And the agent itself chooses training data. So in a few slides, you will see the example that how the agent creates that as the agent move across the environment, based on its movement, it creates the training data. So it is not separately given. And that is one huge benefit of reinforcement learning, that we need not to bother about collect a set of big data and then we will train our model, unlike in supervised learning. Or it is not like that we only have the data and we have to segregate the data like clustering. Rather, we can generate our own training data, and based on that, we can sense the environment and choose what to do. And then it will sound a bit philosophical, this explore versus exploit, and we will see the mathematical formulation of that when we will discuss this multi-arm bandit problem. That this explore versus exploit is that if you look at our everyday life also, and in that we can do whatever we were doing before. But then we all do that, let's do something different. Say, for example, you are coming to here following a specific route, and maybe when you are attending the class every day, you are doing that. But say in the evening time when you are coming for a coffee, you may decide that we every day go through this route, let's go through the jungle and explore a new route. So it is somehow inherent in the nature of human. And that's why when we will discuss about reinforcement learning, as I told during the introduction, that often this is investigated by human psychologists, you will see that we also bring some of this human nature into the agent, that even the agent is very accustomed to doing something, it will explore. The exploration can be wrong, but there is also we will investigate the possibility that this exploration will give me a better possibility. And there will be some very different terminologies, like we already come across these terms in the context of value and policy iteration algorithm, like reward is the short-term benefit, utility is the long-term reward, or in value and policy iteration algorithms, we learn utility from the reward. Then the policy will tell at any state what is the best action to do. And then the state action mapping as the state transition probability matrix. And during Q learning also, you will see that we will define the Q function as a functional on this state and action, or state and action pair will work as the independent variable. So these terms, we already accustomed with some of these terms during value and policy iteration or Markov decision process lecture, but we will utter these terms, which are a bit different than we used in supervised or unsupervised learning, where we mostly talk about training data, feature validation, etc. So this is the basic context, and you will find it's very similar to the what we learned in the MDP class, that there will be a set of states. The state can be, in case of motion planning, that Euclidean position of the bot. Later on, we will also add the orientation or all the 6 DOF of the bot. So for example, if we do reinforcement learning for a fixed based robot, many times it's the end effector position is not only important, but its orientation is also important for task execution. When we are doing a game, then we will encode a particular arrangement of pieces on the board as the state. And a set of actions that what is allowed to do in terms of movement. And in all subsequent cases, we will assume that the set of actions is very limited. Only there are a 2 DOF system. There are 4 actions possible. But then I showed you a case study where we worked with 8 actions, and you can also increase the number of actions when you will actually implement. We only consider 4 actions because it will be easier for us to hand calculate or explain. Then we will talk about the state transition probability matrix. So just to reiterate, this matrix will tell the probability of reaching state S dash when the agent execute action A at state S. So when we learn these BFS, DFS, star sort of algorithms, we assume that it will be deterministic, that if the agent decides to go from one state to other, it will the output of the action will be certain. But in this case of reinforcement learning, or just like our previous value or policy iteration algorithm, we will consider a probabilistic agent, that there will be a non-zero probability that if the agent execute or tries to execute action A at state S, it may not be reach state S dash, it will reach a different state. And then there will be a reward function. So in the most cases, we represent also the reward function as in some of the formulation, you will see that we will represent the reward function as RS. And in some formulation, we also put the A and S dash with the reward function, that what is the reward if the action, like the state transition probability matrix. It has a good advantage that I can use the similar matrix structure to store the reward also. But in some formulation, you will see the reward is only expressed as RS. And the discount factor gamma. So we come across this during the value iteration algorithm. So it's a value between 0 and 1. It can be make 1, but then it will be a complete additive function. So we'll go into, we discussed about the discount factor very briefly during the value iteration lecture. We will further see the effect of gamma in subsequent algorithm. Now, the main difference from the value and policy iteration algorithm is that we do not know the model. Okay, this is unknown to us. So in value and policy iteration algorithm, we assume that we know the model. So you may ask that how do we make the assumptions? But here we will learn that how we can estimate that model. And in many reinforcement learning algorithms, especially the model-based algorithm, you will see the whole algorithm is centered around to learning this model. And once I learn this model, then I will go to value or policy iteration algorithm to find the best policy. And yes, of course, the output of the reinforcement learning will be finding the policy that if I am a state, or if say you are in a particular place in Bangalore city, you know that what to do to reach IISc, something like that. So this will be the setup. So I took it again from the Russell Novick book, and you can follow that. And this is the same setup we used during our MDP lecture on explaining value and policy iteration. That is a 3x4 grid. There, the +1 is a goal state, which is good. -1 is also a terminal state. Both +1 and -1 are terminal state, where if the agent reaches such a state, we consider that this is the end of the epoch or end of movement. And +1 means it's good, -1 it's bad. And the gray color box is not reachable. So you can imagine that this is a pillar in the middle of the room, like that. And the Markov property is, again, please take a note of this Markov property, that the transition probability depends on state only, not on the path to the state. Okay, this is the Markov assumption. And in this lecture, we will not talk about POMDP. So we'll assume that the agent knows where it is at when it is moving. And in terms of action, we will consider the same thing, that if it chose an action, it has 80% probability to follow that action, which is marked here. There are only 4 possible actions, but there is 0.2 probability it will go perpendicular, 0.1 left, 0.1 right. So this assumption we used for the explaining the MDP. But in this case, the difference will be that in the subsequent algorithms, we will consider that we do not know this model. Okay, so we have to learn these values. So next, we will discuss 2 types of approaches to RL. One is the model-based approach, and now I think it's obvious to you that we will try to learn the MDP model here, like the state transition probability matrix, and then we will use the policy evaluation to find the optimal policy. And we will learn 2 algorithms, which is trying to do that in slightly 2 different ways. But then it may happen that the state space is very big, or I do not know the full state space, and then it may not be worthy to know the model for the full state space. I can learn it where we belong to. Like, say, for example, for traveling within Bangalore, you need not to know the or remember all the road structure in the whole India. You can only learn locally in your neighborhood in Bangalore. So these model-free approaches will be that we will try to derive the optimal policy without explicitly learning the state transition probability matrix or the full model. And of course, it's useful when, as I explained, that when the model is difficult to represent and all learn. And this model-free approach, we will learn 2 algorithms. The first will be the temporal difference learning, and then we will learn the Q learning. There will be another type of classification, passive versus active learning. In the passive learning, it will be like that the agent will observe the world and it will get a set of training samples. Each training sample will term it as an epoch. What is the training sample? That the agent, as if it's roaming around the environment, and till it is reaching a terminal state. The terminal state can be either good +1 or bad -1. And it will look at this examples of training data. So here you can find the resemblance to the supervised learning. And then it will analyze these training samples and try to learn the model, or it will learn the neighborhood where it is roaming. But it will not act on the environment when it is learning. So first it will learn, then it will act. In case active learning, the agent will learn as it is acting. So it will learn as it is moving and acting on the environment. So in case of passive learning, we will learn this direct utility estimation, adaptive dynamic programming, and temporal difference learning. All three will be passive learning techniques, as you saw in a previous slide. And the Q learning will be an active learning algorithm, which will also be deriving from the temporal difference learning, that where the model will learn as it is going. And you can readily see the advantage of that, that you need not to collect training sample or wait till you collect adequate sample. You can, as soon as you make your robot and it is ready to move, you can execute that algorithm and learn on the go. So first we will talk about the passive reinforcement learning algorithms, because the active learning algorithms will be built up on the concept of the passive reinforcement learning algorithm. And when we discuss the passive reinforcement learning algorithm, we will again use this grid structure and we will assume that the agent is just following this policy. Just assume that somehow it initialize the policy with these values. And the difference from, again, it's maybe a bit of reiteration, that we do not know this state transition probability matrix. Okay. So that will be the difference from the value or policy iteration discussion that we have. So how we will generate training sequence? So for the model-based learning, first we will talk about model-based learning, then we will go to the model-free learning, that we will learn the model empirically through experience, which means that we will let the model agent to experience the environment. What is by experience? That it will move through the environment, it will get some rewards. Initially, it will not get reward. It will get, once it reach the terminal state, then it will get some reward. And then we will back calculate. And from that, we will try to learn this utility or the state transition probability matrix. And here I put the Bellman update, because just remember it from the policy iteration discussion. So just to explain that this is our state transition probability matrix. This is the policy, and for policy iteration, we randomly initialize the policy, and this will be the reward, and this is the discount factor, and this is the how we update the utilities on each iterations. And as we saw in the policy iteration, just to remind you that we find this equation for all possible state and then we solve it like a set of linear equations. So let us see how we can do that. So this is an example that where we got some training sequence. How? Let us do a, I will just use a different color to make it. So just imagine the agent is experiencing environment, and in all cases, it's starting from this 1, 1. So in the first case, it's from 1, 1, it is reaching to 1, 2 here. So just 1 second, I will just slightly. Yeah. It is going there, and then it is going 1, 3. Then it is going to 1, 3. Then it is coming back to 1, 2. This is the uncertainty. Again, going back to 1, 3. So basically, it's doing a loop here and here. Then it is going to 2, 3, 3, 3 and reaching the goal state here. So next, this is one epoch. This is another epoch. It's starting from 1, 1, sorry, 1 to 1, 2. Then it is going to 1, 3, 2, 3, 3, 3. And then it is, instead of going, it's coming back to 3, 2. Then again, it is going to 3, 3 and 3, 4. Okay, so this is another iteration. And the last iteration is something like that, that it is going this way, then this way, and ending up here and getting this -1 reward. So say for the simplicity, we will consider only these 3 values. Next, what we will do, that here you can see that I just wrote these training samples, these 3 training samples in some bigger font. And just remember that we initialize the reward at a minus 0.4 value. And as I discussed in the previous case, that we will have a more detailed discussion that what happens if we do not initialize the reward at minus 0.4. But for the time being, just consider that the reward values are initialized at minus 0.4 for all non-terminal states. The +1, -1 are the terminal states. Okay. Now let us see what I can do, that we are getting this +1 here. So I can write that I am getting 0.96 here, 1 minus 0.94. So I am just not writing the 0 point here. So we are getting 0.92 here, 0.88 here, and similarly 0.84 and so on. For this, I can again get 0.96 here, then 0.92 here, 0.88 here. And so for the last epoch, we can write the delayed reward or utility like -1.04 or -1.04. And then we can make a table where we can list these state or these delayed reward or utilities. And you may see that there is some repetition of visiting, that this 1213, 1213 is happening twice. So you will get same values multiple times. But we can put all these values in a table, and then it becomes a supervised learning problem that we can feed it to a neural network or any other supervised learning problem, where we will try to reduce the error and try to converge to a set of values of the utilities. So exactly this is done in this direct estimation, where we directly try to estimate the utility. And when they are the rewards are repetitive, that means same reward we are getting for the same state multiple times, so you can average that. So this may sound very intuitive and easy to do, that we have to just go through the training samples or epochs and list the delayed rewards and feed it to a supervised learning problem. And later on, you will see a similar approach when we will discuss the deep Q learning. But this is not the best approach. But and it is very intuitive also. But it does have a problem, that it is not exploiting this Bellman constraint. So in more physical term, what it means, that by putting the utilities values directly to a machine learning supervised learning agent, we are assuming that the utility values are independent to each other. So often when we do statistical analysis, we do it, we collect data and put it in a statistical package. So supervised learning is also a statistical, it makes the similar assumptions that the samples are independent to each other. But in this case, that is not. What I mean by that, that the utility of, say, this state, it also depends on the utilities of the previous states. So by directly estimating the utilities through a supervised learning agent, we are not making these wrong assumptions that the utilities are independent to each other. And we are not using this Bellman constraint. So in the next approach, how we can incorporate the Bellman constraint, in the adaptive dynamic programming, what we do, that we create such a similar table from the training sample, but we prepare the table something like this, or we try to populate. I am just marking it as R dash, which is the utility or the delayed reward, what we got here, these values. So in this case, we are putting this value directly against the utilities, But in the adaptive dynamic programming, what I will do, I will put this delayed award with respect to this table. That say, if I look here, say this is 1, 1, then up action will take it to 1, 2. So I will prepare the table like this, that this is say our state 1, 1. I am going to 1, 2, and I am doing an up action. What is the delayed reward here? In terms of probability, we can, it is something like that, this P S dash given S and A. So we are trying to find this probability, that what is the probability of reaching the state S dash given state S and particular action. Basically, that is the transition probability matrix. And we try to learn this transition. Okay. And yeah, it is simply the fraction of times we see S dash after taking A in state S. Both are same expression. And from that, we put it in the Bellman-Ford update, that once we know the state transition probability matrix, we can use value or policy iteration. So in this case, we use the policy iteration algorithm to get the optimal policy. Problem with this approach is that we have to learn the state transition probability matrix for the whole state space. So in this particular example where we have a 3x4 grid, that is fine. But if it is like a chase or a practical example where you are flying a drone or moving a robot for a slightly larger workspace, learning the full state space becomes very difficult or sometimes impossible. For example, this backgammon game have 10 to the power 50 equation in 10 to the power 50 variables. So many states are there. So what we can do now, the adaptive dynamic programming has a very good advantage over direct utility estimation. So in direct utility estimation, the utility values converge. Converge means they have same values after a lot of training samples, a lot of iterations. In adaptive dynamic programming, since we are learning the state transition probability matrix and using the policy evaluation for smaller state space, if we can do that, we can get convergence very quickly. And you will see the comparative graph very soon in the upcoming slide. But the main problem is learning the state transition probability matrix for the full state space. So an intermediate solution is that we will only learn this state transition probability for our locality or where we are moving. What we define by locality, that we will look at the differences of utilities, like say from one iteration in another iteration, how the utility is changing, or when we are reaching the terminal state, we can back calculate the utilities of the neighborhood. And what we will try to do, that we will not try to learn the utilities values for the whole state space, but for our neighborhood, we will try to bring the unknown utilities to these best values, what we assume or what we can get indication from the terminal state. So we will only work on the localities. How we do that, and here also we still consider that there is we will initialize the policy will still be fixed, that how we do it mathematically. So here you can see this is the previous state, and sorry, I will just turn on the highlighter. So this was the previous state, this is the new state, and this is the policy, and this is the action, the arrows. Okay. So what we will do, that we will update the utility based on this sample change, that we are just changing one action and we are changing the state, and we will update the utility based on the previous utility. So if we look at more, say, a single equation, that this is the new state that I reached after executing this action, like you can consider that S dash state, and this was the previous state UI. So I will update UI based on the utility of the UJ. Now it will make perfect sense if you consider that UJ was the terminal state or +1. So just like in the previous class, if it is +1, you can easily see that I will change the UI to a value so that it has a bigger value, and it will indicate that if I take this particular action at UI, I will reach the terminal state. And similarly, the same principle you can consider this as it iteratively goes down to all other non-terminal state, that based on the action, I will look at the neighborhood and I will try to push the present utilities to the better utility or a desired utility, which will bring to the goal state. Now we talk about this gamma or this learning parameter alpha a few times. So we, in this case, that we will make sure that there can be some cycles you can see that we are circling in the same places. So we can choose the values of alpha or decrease this value for the same state. So if the agent somehow go to the circle and staying in the same state, we will not consider it that much on updating the utility. But when alpha is going to a newer state, we will consider that in our update principle. So this may not be very clear to you right now, that here we will just maintain this table ni, which is the number of times we are frequenting a state. But you can just think that this alpha, what it will do, that if I am revisiting the same state, it will not give me much credit. But if I visiting a new state, it will give me more credit. So somehow this alpha value will encourage exploration over exploitation. And it will be further discussed in the next class when we will discuss about this active reinforcement learning or multi-bandit problem. But presently you consider that in temporal difference learning, that we look at the next state of the utility and modify my present state based on the quality of the next state, and with an aim that I will modify the local utilities to match it our final or desired utility. So this is a comparison of the in the number of epochs, that the number of times we iterate. And here you can see the utility estimation. So in y-axis we put the utility values. So the trade-off is, you can look at these values here: 100, 200, 300, 400, and this is 200, 400, 600, 800. So the temporal difference learning require more epochs or iterations to converge than the ADP. But the advantage is, for each iteration, TD has much less computation, because it is just solving the problem locally with respect to the neighboring states, while the ADP at each iteration, it solves for the full state space. So each iteration is costly for ADP. Each iteration is less costly for temporal difference learning. So if it is a smaller state space, we can go for ADP, where I can take all the state space into memory, because it will give me faster convergence. While in case of TD, if the state space is very large, we can go for the temporal difference learning, because each iteration will be less costly. But with more training samples, I will converge the utility values which I need for the local neighborhood. And there are some problems with the TD value learning, that it's a model-free way to do policy evaluation, because I am not learning the full state transition probability matrix. But we don't want to calculate the value of utility, and from the utility value to find the action using the argmax operation. Rather, we directly want to know the action. So that we will learn in the Q learning. And when I will start active learning, we'll again maybe revisit this slide once more. But for the time being, here is the comparison or summary. The direct utility estimation, this is also model free, because I am not learning the state transition probability matrix. It is simple to implement. Now we directly estimate the utility by solving a supervised learning problem, but we consider the utilities are independent, which is not true. That's why it does not exploit the Bellman-Ford update and often have slow convergence. Where in ADP, we learn the model, the state transition probability matrix, from the sample training data. But it is harder to implement for a bigger state space, because we are trying to learn the whole state transition probability matrix. But for smaller state space, it can guarantee a very faster convergence because we are learning the whole environment in the form of the state transition probability matrix. And while the temporal difference learning, it's also model free. So it's only learning the utilities of the neighborhood where my agent is getting samples from. Each iteration, we are just updating the utilities. It has slower convergence that it needs more training sample. But over time, we can solve the problem in a model free way, exploiting the Bellman-Ford update, unlike the direct utility estimation. So here I will stop the session right now.